Welcome back, guys. Today we're covering 4.7, maxima and minima. I want to do a nice long recall of how this material plays out for one variable calculus so that you can have a refresher. And then we're going to try to extend all of those ideas to multivariable. When you do maxima and minima in one variable, let's say local maxima and minima first, they show you functions like maybe something like this. And they want to investigate points like this point here and this point here. Oops. So if you look, this point is not the maximum of the function. There are values over here that are larger. And this point is not the minimum. There are points over here that are smaller. But what they show you is nearby the point, nearby this first point, for instance, the the function is maximal in the sense that there's a little neighborhood of points, this neighborhood here, for instance, where the function values are smaller than the value at that point. And then down here, there's the reverse thing going on. Nearby, the neighboring values are all larger than this point. And so really, this first point is a local maximum, and this one is a local minimum. When you look at points like these, the first thing they show you is that to have a local extremum, maximum or minimum, you need to have this property that the tangent line at the point is horizontal. So in both of these little pictures here, the tangent line is horizontal. And then they will point out to you that you can also have a point where the tangent line is horizontal. But even though in the first two cases we have an extremum, in the third case, we have neither a maximum nor a minimum, even though we've got that flat tangent line. They go further to say you can also have corners, where in this case you can see there is a maximum or a minimum. But then, of course, a corner is still not sufficient to say whether or not you have an extremum, only that you might. So the methodology or the algorithm technique that they show you to find local maxima minima is first you seek out points where this is true, the derivative is zero, or where the derivative doesn't exist. And then they say a value x, a point x is a critical point if one of these two conditions holds. The idea is that x can only have a maximum or a minimum if x is a critical point. But it's not sufficient that x is a critical point, because even if it is a critical point, you may not really have a maximum or a minimum. Now, there's questions about how you deduce that you do have a maximum or a minimum in general. But in the case that the second derivative exists, they show you something they call the second derivative test. You look at this value here, the second derivative, and there's three possibilities. It could be greater than zero, it could be less than zero, and it could also equal zero. If it's greater than 0, then you've got this phenomenon where it's curving upward. And if it's less than 0, there's this phenomenon that is curving downward. And so in the first case, the second derivative test tells you you're at a local minimum, excuse me. And the second case here would tell you that you're at a local maximum. And then the last one is inconclusive. This test doesn't work. You would have to do some other test to determine whether or not you actually have an extremum. But we won't care so much about that right now. We're more interested in the case where the function is twice differentiable. So this right here is a quick sketch of what you would have learned in a one variable differential calculus class for finding extrema, local extrema. First, you find the critical points. These are points where the slope is 0, the tangent line is 0, or there's a corner. And then you do some further analysis to figure out, hey, is it really bending up? Is it bending down? Or can we not really tell? So we want to extend these ideas to multivariable. Let's take a crack at this. I'm going to start by just drawing the relevant or the corresponding analogous pictures for 2 dimensions. So let's go to this a little bit to the left of that. So we can come up with 3 analogous pictures to the ones I've already drawn. I'll do a different color now. It can bend upward and bend downward. You can also have a saddle point. Uh, and for each of these 3 cases, there's a point. There's one there, there's one there, and this one's harder to draw. The way I've drawn it, maybe it's somewhere like right here. And in all 3 cases, you've got a horizontal tangent plane. In the first case, all of the function values are above the tangent plane. In the second case, they're all below. And in the third case, they are neither all below nor all above. You have a little bit of both. And in the first case, we would identify this as a local minimum, the second one as a local maximum. And then this third one, the word we use is a saddle because it looks like a saddle. And you have neither a maximum nor a minimum. So the picture is very much the same. It's just a little more complicated with the extra dimensions, or dimension in this case. Now, we saw in the last lecture that if the function is differentiable, the gradient has to be 0 if we have a horizontal tangent plane. If we have a horizontal tangent plane, the gradient's got to be 0. There's also the possibility, instead of having a tangent plane, that we've got some kind of a corner, a higher dimensional corner like a cone. But we'll start with this here. And so if we're at a minimum or a maximum, so a local extremum, let's say, we're going to need this to be true. The gradient is 0, or maybe there's a corner. So we start by defining critical points in higher dimensions. Let's go ahead and just say we have a point, x initial, y initial. And then this is a critical point of f, the function f, if one of these things is true. Either the gradient at this point is 0, or fx at that point, the first derivative in the x direction, and or fy doesn't exist, doesn't or don't, right? Doesn't exist. So just like in the one variable case, being a critical point is enough to only to say you may have an extremum, but not necessarily that you do have an extremum. So let's just start with this. There's one more thing I should say here. A point is a critical point. I can say this too here. We're only interested in points where neighboring values exist. So if you recall from when they teach you, first they teach you local extrema, and then they teach you absolute extrema. If you're in a case where you have a function like, let's just say, like this, it's just defined on an interval. And at the edge, you have a place where the tangent line is horizontal. We don't include this as a critical point. This is like an edge point. We deal with the edge points later on by other methods. So over here, it's a critical point if this is true, and I'll just put this one more thing. And this point is in the interior of the domain of F. Okay, so we'll start today with just this goal, the goal of identifying critical points for a function. Just get a couple examples out of the way for this. Now I'm going to warn you, the book kind of went pretty hard on these examples, so it'll take a bit of math to get through these, but you do want to make sure you're able to do these problems. So here's the first function they give us. I'm going to put a square root over this in a second. 4y squared minus 9x squared. Plus 24y plus 36x plus 36. They ask us to identify the critical points of this function. So we can start off by looking at what the gradient of this function is, since we want to know where it's either the zero vector or where it doesn't exist. Well, let me work out the two derivatives separately. Let's try just f sub x first. If you differentiate this, this whole expression goes in the denominator. So I'm going to just write it this way. But that whole square root of whatever goes in the denominator. And then on top, if we differentiate with respect to x, we get negative. So it's going to be negative 9x plus 18. If you differentiate this, you get negative 18x plus 36. But there's a 2 in the denominator coming from that 1/2. So you get negative 9x plus 18 in the end. If you differentiate with respect to y, still in the denominator, you're going to have f of xy. In the numerator now, we get a 8y plus 24, but that gets divided by 2, so 4y plus 12. And to find to find the critical points, we can start by trying to simultaneously set each of these equal to 0. That's the same thing as saying the gradient is equal to 0, or to be more specific, the 0 vector. And this gives us a system of equations. We can simplify these. Negative x plus 2 equals 0, and y plus 3 equals 0. In the second equation, I divided by 4. In the first equation, I divided by, let's actually do negative 9. So there's only one point where both of these equations are true, satisfied. X equals 2 and y equals negative 3. Let's be clear what we've done so far. We're looking at a function, and we've gone and said, well, where is the gradient of this function 0? If x equals 2, and y equals -3, so somewhere like right there. The gradient of the function is 0 here. There's also the possibility that one or more of the derivatives doesn't exist. The only way that can happen is if one of these the denominators is 0. And now there's an issue here. It's kind of a subtle issue if you're not used to this stuff, but this function is not defined when what's under the square root is negative. So anywhere that the function equals 0, where f equals 0, is a boundary point. So I'm gonna say this way, and this is actually an error in the book. So I'll put it like this. Note, if fx or fy is undefined, then the function f of xy equals 0, and that implies that xy is on the boundary of the domain of f. So automatically it can't be a critical point because we said we need to be in the interior of the domain. So the book says this. The book makes it clear you can only be a critical point if you're on the interior, but then it falsely goes on and says, well, there are all these places where the function is 0, and those are on the boundary. And it even says, like, those are critical points on the boundary. So they contradict themselves. That's not correct. Let's just be clear about that. This function has one critical point where x equals 2 and y equals -3. Now, I want to go further into the picture because you should be able to draw pictures like I'm about to draw, and it's going to make clearer everything I just said. What does the domain of the function f look like? So we need to find all of the points where this whole expression is greater than or equal to 0. That's going to be the places where the function f is defined. Now, there's an issue with the algebra here. You do have to get good at this over time, but you take the 4y squared and the 24y, you group those and pull out 4. That gives you y squared plus 6y. And then you complete the square by adding in 36. Now, you have to not forget that you added in 36. Sorry. By adding, well, you add 9 here, right? But then 9 times 4 is 36. So we really added in 36. For x, you can pull out -9, and you'll have x squared minus 4x. And to complete this square, we have to add 4 here. But we really subtracted 36, so it's nice. Those actually cancel each other out. So we can put that last little bit of 36 right there. And this whole thing's got to be greater than or equal to 0. So one more time, let me just be clear about what I just did. Just because you do have to develop this skill if you haven't already. This and this together plus 36 gave me this. This and this together minus 36 gave me this. Luckily, those two numbers canceled out, the plus and the minus 36, so I don't have to worry about those. And I've got one more extra little bit of 36 on the right here. Now, I like this form because I can rearrange things, and this all comes out to be 9x minus 4 squared minus 4y plus 3 squared. That's x minus 2, sorry, is greater than or equal to 36. Whew, that's a lot of work. I'm going to just leave you one moment to think. What is that shape right there? Or let's set it equal. So if we do 9x minus 2 squared minus 4y plus 3 squared equals 36. Actually, divide across by 36. This is the standard form. What is that? It's a hyperbola. And it represents the boundary of the domain of f, the function f. Whoops. So there's this point, uh, 2, -3, right there. If you plug in 2 for x and 3 for, no, -3 for y, these both come out to be 0. And now if you go up by 2 in x, fixing y, or down by 2, you get these 2 points. And you ultimately generate a hyperbola. I'm just going to sketch it roughly like this. Whoops. This is the hyperbola that we just found. And the domain of the function f is all the points in here. This is a lot to visualize, but going back to the problem that we started with, we found one critical point, this place where the gradient is 0. This is this point right here. And then we found these other points, these places where the denominator here and here is 0, making the derivative undefined. But we just make a note, we acknowledge that we're on the boundary, and those are therefore not critical points. We don't have to include them in our analysis. They are not a part of what we're doing. So you would simply say 2, -3 is the only critical point. So let me just zoom out. If you were doing a problem like this, I want to see all of this here. You don't have to go this far to sketch everything. You should be able to visualize it and make this case here that, there's these boundary points. But you don't have to draw these things. And I guess for a problem like this, you don't even have to work out that this is a hyperbola. It's very useful information, and it might come up for harder problems later on. But for this problem, you just have to know that those are boundary points. You don't have to know what the shape of the boundary is. That's my first example. Let's do one more, and then we'll continue, because we really care about extrema, not merely critical points. Here they give us another function g of xy, and this guy is x squared plus 2xy minus 4y squared plus 4x minus 6y plus 4. Okay, no square roots, no denominators. This is a polynomial. This function is defined for all points in the real plane. So we don't have to worry about boundary points. And it's also differentiable everywhere. So we don't have to worry about corner points. So to find the critical points, we only need to look at where the two partial derivatives are simultaneously 0. The first one is 2x plus 2y plus 4. And then the second one is 2x minus 8y minus 6. And these both have to be 0 at the same time for us to be at a critical point. Let's make these a little simpler. X plus y plus 2 equals 0. X minus 4y minus 3 equals 0. Just want to make sure I'm not making any mistakes. 2x plus 2y plus 4. 2x minus 8y minus 6. And then we reduce them all. 1, 1, 2, 1, -4, -3. Yeah. Okay, we're going to solve these at the same time. Let's go with, I don't feel like doing this. Subtract the second one from the first one. So we get 5y plus 5 equals 0. Y equals -1. And then we'll plug that into the first guy. X minus 1 has to equal -2. X equals -1. So there is only one critical point because this pair of equations only has one solution. So -1, -1 is the only critical point. Okay, so that's two examples where we basically, most of the work is to find these two equations, set them both equal to 0, solve simultaneously, and that's more or less your critical points, at least when everything is differentiable. Let's go over here, I guess. All right. Yeah, so now they want to rigorously define the word saddle. Let's just get this out of the way. A point x initial y initial is a saddle if uh, x initial y initial is a critical point. Sorry. Where is the, hold on, sorry, 1 second. I want to use their notation, but okay, well, whatever. It's a critical point. X initial is a critical point, but neither a local maximum nor neither a local max nor a local min. And it's a maximum. Yeah, it's a maximum if there's okay, what might as well write it out. X initial, sorry, I should have put in these two first, but they're kind of self-explanatory, is a local max if, so here's your point, if there's a little region, and in that region, F is biggest at this point. So it's a local maximum if there is a small disk. We'll just call the disk D, centered. It doesn't really have to be centered, but whatever, centered at X initial, Y initial, and F of X initial, Y initial is an upper bound for the values of F for any other point X, Y in the disk. And then I'm just going to put this is a local min, and I'm going to write the word similarly. Everything is the same, but you switch this inequality. Okay, so a point is a local maximum or a local minimum if these two things are true. And then it's a saddle point if it's a critical point, but it's not a local maximum, and it's also not a local minimum. So those are the three things we care about. Given that something is a critical point, how are we going to tell which one it is? So this is kind of another one of these things. It's kind of rough to teach it because it requires maybe some linear algebra or some degree of further analysis that we don't really expect students to have necessarily when they take Calculus 4. So we don't really teach it. It's not that crazy, not that hard to understand, but nonetheless, I'm not going to explain it. I'm only going to say this. Think like this. Right? For a function of one variable, we know what the second derivative test tells you. It's either concave up, it's either or concave down, or it's neither. And so instead of this quantity here, it's a more complicated quantity. Here we go. F sub xx, this is the second derivative in the x direction, times the second derivative in the y direction. And then you've got to subtract off the second derivative, the mixed one, squared. So I'm squaring the whole thing here. I'm going to give this a name. They call this, I'll use a capital D for the discriminant. I'm going to use a lowercase d because I've been using a lot of capital D's. And let me say of x and y. So let's just freeze. This here is the discriminant. Let me just check. They do call it that for this stuff, right? Oh, they don't give it a name? Oh, they do. Okay, discriminant. Yeah. This is the discriminant. Discriminant. So let's just freeze here. This is the discriminant. And here we go. A critical point xy of a function f is a local min if the discriminant at that point is greater than 0. This is the same as if the second derivative is greater than 0. It's the same idea. It is a local max. Oh, sorry. If d is greater than 0 and let's say this. I'm going to explain this as best I can in a second. A local max if the discriminant is greater than 0 and oh, I did it backwards. Sorry. Ugh, I'm sorry, guys. I'm messing this up. Greater than 0. One more. And not sure. Wait, sorry. One more. What did I? A saddle. And then we'll do not sure next. A saddle if the discriminant is less than 0. And then what does it say? Unsure or unclear if the discriminant is 0. Okay, I'm going to try to explain a little bit about what's going on here. The first case is, let's go with local min. For a local min, if you try to analyze the second derivative in the x direction, it's concave up. That's f sub xx is greater than 0. And in the y direction as well, it's concave up. And that's f sub y is greater than 0. They're both greater than 0. On the other hand, if you were at a local maximum, the second derivative in the x direction would be negative, and the second derivative in the y direction would also be negative. So let's look at what this means. Either they both bend up and it's a minimum, they both bend down and it's a maximum. In either case, the product of the two has to be positive. So either they're both negative and you get something greater than 0, or they're both positive and you get something greater than 0. It's the third case that's something different. In the third case, the case of a saddle, you'll have one direction. Let's try and see if we can do this right. One direction bends down and one direction bends up. And this gives you that saddle. And if this is X, this is Y, one direction bending down is like the second derivative is negative. The other direction bending up, the second derivative is positive. And then the product of these two is negative because, one of them is positive and one is negative and one is positive. Now, there's a third issue, and this is the part that's kind of hard to get new students to understand why it is that we don't just use this, but we also have to subtract off this third thing, f sub xy squared. Um, and I'll just make a quick note. This is the determinant of a matrix. Um, and I'll say we need linear algebra to talk about this. Need linear algebra, which we don't assume. So I'm just going to put this dot, dot, dot here. This picture is sufficient. You're calculating a quantity. We're calling it D. And if it's positive, if D is greater than 0, every direction bends up. If D, every direction bends up or every direction bends down. So these first two here together are where D is greater than 0. Either everything bends up or everything bends down. In the case of the saddle, some directions bend down and some directions bend up. When the determinant of this matrix, so what we're calling the discriminant, when this is negative, it's because there is this product going on where some directions are negative and some directions are positive, and D comes out to be negative. When all the directions agree, they're either all positive or they're all negative, then this D comes out to be positive. If you go back to the second derivative test, D positive, you can't tell if it's a minimum or a maximum. You have to do a little bit more work. It's right here. You just check. You can also instead check the other one, F double, two derivatives in the Y direction. You just need to check one of them, either one. Because if the discriminant is positive, then both of these second derivatives are positive or both of these second derivatives are negative. Let's just review one more time. You find this discriminant D. If it's 0, we're unsure, like in any other second derivative test. If it's 0, we throw out the whole process. If it's not 0, then it's either negative and we have a saddle, or it's positive and we don't have a saddle. Once it's positive, there's this extra work. Does it bend up in every direction or does it bend down in every direction? Let's take a crack at what am I trying to say? An example problem and see if it can make some more sense. All right, we'll go over here. Come on. Sometimes this thing. All right. Example. Four x squared plus 9y squared plus 8x minus 36y plus 24. And we're asked to find the critical points and use the second derivative test to identify the local extrema. So again, this function is defined for all points in the real plane, and so are the derivatives. We don't have to worry about corners. We can start by finding the critical points of this function. There's only one. These equations are simultaneously solved when x equals -1 and y equals 2. So -1, 2 is the only critical point. Is it a local maximum? Is it a local minimum? Is it neither? Well, if it is a local maximum, then every direction bends up. If it is a local minimum, then every direction bends down. In both cases, the discriminant will be positive. So we want to find that discriminant and take a look at it, see what it is, so we can know. The second derivative in the x direction is 8. The second derivative in the y direction is 18. The mixed f sub xy is 0. Keep in mind, this is the same thing as the other mix, f sub yx. We saw that Clairaut's theorem. The discriminant at any point is 8 times 18. We don't care about what this number is. We just care about what sign it is. It's positive. Because that's positive, any extremum must be a minimum. And this tells us -1, comma 2 is a local, excuse me, minimum. Minimum. But that's that whole problem there. I know it might seem like a lot of work. It's definitely very calculation heavy. But there's really just these two steps here, right? You've got to find the critical point or points and check this quantity D at every one of these points. And depending on what that quantity is or what the sign of that quantity is, you can assert if it's a maximum, if it's a minimum, if it's a saddle, or inconclusive. Let's try another one. Hopefully this one's a bit more exciting. Yeah, this one will be. Okay, they give us G, 1/3 x cubed, 1/3 x cubed, plus y squared, plus 2xy, minus 6x, minus 3y, plus 4. Yeah, okay, good. When you see that higher power there, that 3, you know it's going to be more interesting. When it's just a quadratic, everything up to power 2, you're always just going to have this one critical point. Once you go up in powers, things can get more interesting. Okay, let's find all of the critical points of G. Did I get that right? X squared plus 2y, oh, minus 6. And then gy is 2y plus 2x minus 3. We need both of these guys to be 0 simultaneously. See? I'm going to solve for y in the second equation. Y equals 3 minus 2x over 2. And then I'm going to plug that into the first equation. X squared plus 3 minus 2x minus 6. Because that 2 right there cancels with that 2 right there. And we get x squared minus 2x minus 3 equals 0. X minus 3x plus 1. So x equals 3 or negative 1. If x equals 3, we're going to use this right here. 3 minus 6 is negative 3, so y equals negative 3 halves. If x equals negative 1, then this is 3 plus 3 is 6, divided by 2 is 3, then y equals 3. I did that wrong. Negative 1, negative 2 is plus 2 is 5 halves. So we've got 3, negative 3 halves, negative 1, 5 halves. These are the critical points. All right, that's the first half of the problem. Right? We've found the two critical points. We don't necessarily know that either one is an extremum yet. We must continue. Before we plug in the points, let's find the discriminant. I need to know what the second derivative in the x direction is. This is going to be 2x. Second derivative in the y direction, just 2. And the mixed derivative, which is also 2. Okay. The discriminant, it's the product of these two, so that's 4x, minus this one squared. Come on. At the first point, something. 1 second, sorry guys. Okay, 1 second. 1 second. My laptop's getting hot. I gotta put something under it so it can breathe. Okay, at 3, negative 3 halves, what is the discriminant? Well, x is 3, so this is 12 minus 4 is 8. This implies f has a local minimum at this point. The other point was negative 1 5 halves. At this point, the discriminant, well, x is negative 1, it comes out to be negative 8. And then this implies that f has a local max at this point. Okay, we're done with that problem. We got them both right here. Perfect. In both cases, and in every case for these second derivative test problems, you find where the two first derivatives are simultaneously 0, that's your critical points. First case, we found 1 point. In the second case, we found 2 points. Then you go to each of the critical points and check the discriminant. Over here, there was 1. It was, oh, I can't believe I just did this. Sorry. Oh, I'm terrible, 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 terrible. See, you do these things a million times. You just don't even think. I didn't even do the second half. So over here, the discriminant is positive and the second derivative in either direction, let's just do this direction, is greater than 0 because it's equal to 8. Okay, so this is a local minimum. Over here, oh my God, what a terrible, terrible mistake. I'm on semi-autopilot. Over here, we also need to check what the second derivative in one direction is. Let's just do the y direction because that's easier. It's greater than 0. It's equal to 2. So again, this is a local min, and this is totally false. I'm just totally on autopilot. Jeez Louise. It's negative. It has a saddle. F has a saddle. Terrible, terrible, terrible mistake on my part. Okay, well, we had one place where it was positive. That's either a minimum or a maximum. We don't know. We need to check one of the second derivatives, either yy or xx. That being positive made it a minimum. If that was negative, it would be a maximum. Then this one down here, the discriminant is negative. It's a saddle. It's neither a maximum nor a minimum. It doesn't matter what those guys are. A million apologies. I really hate making mistakes like that. Okay, let's see where we are. All right, what comes next? Right, absolute extrema. Okay, that's critical points. That's the interior. Those are local extrema. Now there's another question. I'll draw it as a picture before anything else. So this is the next part. This is a whole section. Absolute extrema. Here's the picture to have in mind. Well, there's a lot of pictures you could have in mind. But let's go with like this, the upper half of the sphere again. That top point there is not only a local maximum, but it's actually the absolute maximum. The domain of this function is only this disk. And the biggest this function gets anywhere on this disk is right there at the top. On the other hand, all along the edge here are all absolute minima. All along this red edge, the green function is 0. None of those are critical points. They are not in the interior of the domain. The derivative or the gradient is not 0 at any of those points. Those are absolute extrema because they are the smallest the function gets anywhere. So those are absolute minima. And this guy here is both a local but also an absolute maximum. We begin with a theorem. We don't prove this, but I'll state it as a theorem. And I'll draw a picture like the purple disk. It doesn't have to be a disk, but it's some domain with the following properties. If the domain of F is closed and bounded, So it can't be the whole plane. I'm going to put dot, dot, dot. Here's some closed bounded domains. That's a closed bounded domain. That's a closed bounded domain. That's a closed bounded domain. Put a little hole in the middle. That's a closed bounded domain. And I'm going to put the word not. Not a strip that goes on forever in both directions. Not the interior of like that hyperbola, those two hyperbola. Not the whole real plane going on in every direction. Those are all not bounded. And there's the issue with closed. I won't worry about that so much. I think they'll all be closed for our examples. But on domains like the purple ones, the following theorem, what I'm about to write, holds, not on ones like the green one. So if the domain of F is closed and bounded, here is the statement. F attains an absolute maximum and an absolute minimum. Absolute minimum. A quick explanation for y for one variable. Here is a function whose domain is not bounded. It has a horizontal asymptote. It never reaches that value. There is no maximum. It just gets bigger and bigger and bigger. But on the other hand, if we have a function, I'll do a purple again, and the domain is bounded and closed, and it tries to do something like that, it's going to go up like this and this. It's got to stop somewhere. And similarly on the other side, it's got to hit some end. And so we reach these. This is kind of the meat or the insight of this theorem. When the domain has complete edges, it's totally blocked in every direction. F can't be sneaky. Oh, and there's one more thing. If the domain of F is closed and bounded, sorry, and there's one sneaky little extra thing here, and F is continuous. We can't have if F is allowed to break, then obviously it can cheat. So no cheating. Okay. If F is continuous and the domain is blocked in on all sides, so there's no runaway nonsense going on, then F has to hit its maximum and it has to hit its minimum somewhere. It could do it on the inside. That's fine too. But if it doesn't do it on the interior, then it does it somewhere on the edges. So that's a theorem. It actually takes a lot of math to prove that, which we're not going to do here. But we are going to use it. So here we go. This is the culmination of the first half of this term, really. Finding extrema. Here we mean the absolute extrema. So let me put the word absolute. Absolute on a closed bounded domain D. Here are the steps. So think about it like let me do one more picture to really aid in what we do here. Here's we're just going to draw a function. It'll have a domain like this. There's the domain. And then let's give it some critical points on the interior. So here it bumps up, here it bumps down. So that's a little mountain. That right there is maybe a saddle. That's another mountain. Maybe somewhere else, it's got a little valley. So there's a little valley right there. And then on the edges, maybe it goes to 0. And then maybe on some places it gets really small, like down there. So you look at something like this and you say, well, that could be the absolute maximum. That could be the absolute maximum. It's probably this one. That right there doesn't look like it's the absolute minimum. The absolute minimum looks like it's down here somewhere. And then unfortunately, there's these issues. Like there's that point. It's a critical point. It's not going to turn out to be either, but we don't know that in the first place. So what do we do? Here is our steps. One, Find all critical points. These are the red dots there. Find all critical, geez, all critical points. 2, classify them. You don't even actually, you know what? Honestly, you don't need to classify them. I'll say why in a second. Find the value of f, find the values of f at these points, the values of f at these points. There's a separate step. We're going to have to talk about how to do this. Calculate the max and min of f on the boundary, max and min on the boundary. And now you've got all these values. You've got all the critical values on the interior, right? Like you could find this point, this point, this point, this point. And then on the edges, you're going to find some other points. And then the bottom line is the biggest is the maximum. The biggest of all of those is the maximum, absolute maximum. And the smallest is the absolute minimum. So why don't I have to check why don't I have to check the classify the interior points? For absolute extrema, we don't care. Like if that one is a saddle, that value will never be the maximum. So when we check it, we're going to get some number. It's not going to be the biggest one. So in the end, we're going to ignore it. In that sense, it's a waste of time to classify it. You could classify it as a saddle and throw it out and say, hey, it's a saddle. That's not a minimum or a maximum. But that's a waste of time because you're just going to say, well, whatever the value is there, I found this other value that's bigger. That's definitely not the maximum. Who cares? So you can check them if you want. You don't have to. Okay. So one more time. From a bird's eye view, what you're doing is you're checking for the interior, and then you're also checking for the boundary. The first 2 steps, 1 and 2, are how we check the interior. We find the relevant points in the interior, check their values. The third step is we have to check the boundary somehow. This will be easier. When we're done, we're going to have all these candidate values, maybe like a 1, a 3, a 13, a 27, and a negative 100. You'll just pick the biggest one and pick the smallest one. Those are your extrema. I think here I'm probably at about an hour. So I'm gonna stop here and I'll pick up I'll pick this material up tomorrow and hopefully get as far as I can through the Lagrange multiplier stuff. I suppose for right now there are no more announcements that I have to make. Please let me know if you're keeping up, if you have questions, if you have concerns. To be entirely honest with you guys, I haven't had anybody come to office hours yet, which is perfectly fine with me. But I want to stress that if you feel like you need extra help or you're struggling or anything like that, the whole reason for the office hours is that. So if you do want any kind of extra, um, time to talk through these things, just come on and say hi to me, and we can do that. All right, thanks, guys.